Can you guys see my screen?
Yes.
Okay, great. So yeah, just some information for those who want to sign up for Data Science Club. And so today we'll talk about adversarial attack, and I'll be given a gentle introduction to that. And I'm Arthur Chen, and this is today's agenda. So we'll be talking about what is an adversarial attack and why we learn it. So what's the motivations and how to attack. And we'll talk about different attack methods. So what is an adversarial attack? Suppose we have an image classifier that tells you if an input image is a cat or a dog. So let's say it's network, and we give an image, like a dog image, to the network, and non-surprisingly, it gave us a dog as the model's prediction. And however, let's say if we add some noises to the dog image and feed into the network, it gives us something else, which is unexpected. So there are two types of adversarial attacks. One is non-targeted and one is targeted. Non-targeted is basically you feed in an image and you want to, your expected outcome would be anything else other than dog. And for targeted attack, you want to misclassify an image as a special class. For example, I want to classify a dog as anything else, such as a cat. And motivation for this is that we seek to deploy our model in real life. And in real life, you have those malicious attacks, especially for big companies. And people can maliciously fool our system to achieve their purposes. And we can defend our ML systems by knowing the theory of adversarial attack. So how to attack? Let's say for an image classifier, we have three classes: dog, cat, and fish. So the above image is the prediction, is the distribution of the prediction for one instance. And the bottom one is the distribution of the prediction for another. And let's say we have an image, a cat image called x0 or x0. We feed into the network F, and we get our y or our prediction y0, and it is basically equal to function f taking x0 as our input. And let's see, we fit in an image x, we don't know the image. We fit into the network, and we want to get something else for non-targeted attack. And we want to achieve this kind of final distribution for our model's prediction. And to misclassify it, we want to make those distributions to be far from each other. So the prediction, the distribution of y as far as it could from this perfect distribution, which gives us 100% confidence in cat. And for targeted attack, we want those two distributions to be as close as possible. And y target may be, let's say, 100% confidence in dog. And how to attack mathematically, it's basically an optimization problem. So let's say we want to find the x such that it has the minimum loss. So L stands for the loss function, and x is basically the input. And y and x arrow star is the x we want to get. And for non-targeted attack, the loss is basically is equal to negative e given y, which is the prediction, and y hat is the desired prediction. And why would put the negative sign in it? Let's say if e is our cross entropy loss, you can think about it as the distance between your predicted image and the actual image. So we want to be as far as possible. So we put a negative sign in front. And for targeted, it's basically the same loss function plus another item where we want the output to be as close as possible to our desired output image, output distribution, y target. And we apply a constraint on it where the distance between our input image and the actual input image is less than epsilon. So what does this mean? That means if we have an input image of a cat, we don't want to make too much modifications on it such that human would notice the difference. So if we were to facilitate attack, if someone can easily distinguish your attack signal, then they can just do something accordingly. So we want to make the input image to be unnoticeable by human. And that's basically non-perceivable. So how to tell mathematically if the noise is perceivable? So as I said previously, we want to minimize the distance between our input signal and the actual input image to be less than epsilon. So it's basically the difference between those two vectors. If we were to flatten our input images, which is a 2 by 2, which is a m by m or m by m matrix. So there are two functions we can use. One is called the L2 norm, and it has the following expression, and the other one is L infinity. So we want to take the maximum absolute value of delta xi to be the loss for L infinity. So why is that? And we'll see. Let's see, we have an image only 4 pixels. And if we were to apply some modifications on it, for example, if we change every pixel a little bit, and it will give us the above image. And if we only change 1 pixel by a large amount, and it will give us the bottom one. So for the image above, it is pretty hard to tell the difference between the original image and the modified image or the attack image. And however, for the bottom one, it is fairly easy for most people to tell. The green pixel it is weird. It is totally different than the original image. And however, if we were to use L2 norm as the criteria, we will notice they are the same. And if we were to use L infinity, we will notice the one below has a very large L infinity value. And also we will need to consider human perception. For different groups of people have different perception abilities. And L2 norm and L infinity may not be able to get applied to audio systems or speech processing systems. And let's look at the implementation. If we were to use this and deploy it on our own model. So it's an optimization problem. We want to get the minimum value of X error star by solving this problem. And however, it is probably very hard to solve it if we were to solve it directly. And then, however, if we remove this constraint, it looks familiar. It is basically the old-fashioned gradient descent, where we solve W weight, B stands for bias in this optimization problem. But in this case, we're solving for X, which is the input, not the weights and the biases. And this is just a normal gradient descent. And if we start from original image X naught, we can do an iteration to improve our input image. So xt is equal to the previous image minus eta g, and eta is basically the learning rate and g is the gradient. It is basically the same gradient methods we use for other classic neural networks. So we update the input instead of the parameters. And if we apply these constraints on it, it's just an extra step. So we only check for each update, we want to check the difference between the current xt image and x0, which is the initial or the original image. We want to make it to be smaller than epsilon. So if it is greater than epsilon, we do something. So we fix our current step xt. So how do we do that? Let's say here's the optimization landscape. We landed at the red dot after update, and we can see we want to make sure our xt is within the blue box. So how we fix it? We just drag it towards x0, and that's it. So there are two types of attacks. One is called white box and attack, and the other one is called black box attack. So in the previous attack, we know the parameters of our network, and this is called white box attack. And however, for most APIs, you won't be able to obtain the weights and even the training data. So how would you able to attack a model without knowing the parameters or even the training data? And black box is possible. So suppose we have a network, the black box network, how would they be able to attack it? And if we have the training data, we can basically fit into the black box network. So by calling the API, for example, and you get your output image or output data. And however, if we were to, we can just train a proxy network that mimics the behavior of the black box network. We will be able to gain some useful insights and generate some possible attack images. So we use the proxy network to generate attacked objects. And let's see if we feed our fake cat into the proxy network and we were success on this attack, then we can possibly feed that to the black box network and be successful. But for most cases, we don't have training data in this case, in other cases. So how would we be able to do that if we don't have the training data? And so one possible solution would be feeding random images to the black box network. And since it is an API, it will give us something. And we train the network based on our random images and the output from the black box network, and use that as our training data to train our proxy network. And let's see the results from that. So is it really effective? So we have a chart for that. The x-axis would be the attack networks, and the columns would be proxy networks. So what does this mean? Is that network with lower accuracy would result in more successful attack. So if you can see the diagonal vector, it's all zeros. That means if we were to use exactly the same networks for our black box attack and proxy network, then we would end up with a very successful attack. And however, if you look at other networks, such as ResNet 50, if you were to use ResNet 101 to be your attack network and train the network using ResNet 50, you'll still be quite successful, ended up with an accuracy of 20%. And in order to how to improve our attack, we can basically put multiple models and stack them together in order to achieve better results. And as we can see, all of the trials were very, very successful, ended up like near zero accuracy by the end. So here are some other attack techniques. So for previous attacking methods, we basically generate a totally different noise map to each image and apply it to the original image in order to facilitate a very successful attack. And for this method, it only uses one pixel to attack successfully. So we can see here's a cup. We put a black dot in a red circle. It ends up with a soup ball. And for the left bottom one, we add one white signal, and it ends up to be a joystick. And how is it possible to be a joystick? It is actually very similar if we were to look at it this way. And the other method is called universal attack. So as I mentioned, previous methods requires a totally different signal for each image. So for example, we have 200 images and we want to facilitate 200 attacks, then we would require 200 different images. And thus we want to run the model 200 times. And if the data size is go up by 10 times, then we would need to have a 10 times larger runtime. And this method basically uses one signal for all attacks, no matter what kind of input you have. So we can see in an image for the joystick, we apply the same signal and get a chihuahua. And something beyond images. So adversarial attack can be applied to different domains other than computer vision, such as speech processing and NLP. So here's an example from the SQuAD dataset. So SQuAD dataset is basically a Q&A dataset for natural language processing. And here's one of the data instance. So let's see, we have the question, why did he walk? And given the context for exercise, Tesla, blah, blah, blah. We have the document below. And the model's prediction for this one is exercise. So the answer for why did he walk is basically exercise. And however, if we were to add one more sentence on this, so let's say why, how, because to kill American people, and the model's prediction would be totally different. And for all the data, all different data instances within this data set, we apply, we just add one more sentence, we would be able to achieve the same results. And this is actually a real attack. If you're interested in this, you can just check out the reference link. And that's everything for today. And for any questions.
Could you go back to, I think the slide with the loss function on it, or like
this one?
Further back. I'm a little confused about the training procedure.
Oh, the training procedure. This one?
Sure. So I understand the idea of if you don't want to change the parameters, you want to change the image. So here we only need the function. And so my question, earlier you brought up gradient descent. Are you applying gradient descent to change the image?
Right. Yeah, I see what you mean. So basically this function, right?
Okay.
Yeah, basically back propagation. You can think about it as doing back propagations. However, for example, you have a 3-layer network. For normal gradient descent, you would apply for 3 different layers, but for this one, you apply for 4 different layers because you have to consider like the input layers as well, right? So basically, like adding more layers to optimize. Yeah. So let's say if you have a 3-layer network, an input layer, a hidden layer, which is the middle whatever layer, right, and the output layer. So normally, if you were to compute, if you were to optimize using normal gradient descent, first you put an image, right, forward it and get a result, and then you get your y and feed y into the loss function, right? And that'll give you some values, but that doesn't matter because we only need the process. And using that, we can backpropagate it using a chain rule, right? And thus for each parameters, and even for the input parameters, we have a gradient values, right?
Yeah.
And for backprop, we basically propagating it backwards to the input layers, including the input image. And then we just apply the gradient. Here's G, see?
Right.
Yeah.
But so here you're not applying like when you say the parameters, is that supposed to be the parameters of your proxy model?
Right. Yeah. Yeah.
And and then you don't want to update the parameters of the proxy model.
Sorry.
Just
like for input, we don't do that. Like we update our parameters using different. I mean, for each layer, it has a gradient. For normal gradient descent, we have gradient for input, but we don't apply it.
Yeah.
Right. But for this one, we apply. Sorry. Yeah. Might be a little bit confusing. So we apply. We do apply gradients to parameters and update them. But that includes the input parameters as well. Yeah, it might be a little bit it might be a little bit confusing here. I mean the green text. Yeah, I should remove it.
Are you updating both the proxy model and the input?
Right.
Oh. Why do you update the proxy model?
Because you want your proxy model to learn, right? So without knowing the gradient, like without optimizing your model's parameters, right? You won't be able to learn from any like input images. Like your model, your proxy model is not evolving to learn the patterns. I mean, the whole process is basically kind of similar to like a kid learning how to learn from a teacher. And basically what like all he does is basically mimicking the teacher, right? In this case, like the proxy network is what it does is basically mimicking the behavior of the teacher network or the black box network. Yeah,
so okay, if you had the original network, would you still update the parameters of the original network?
The original network?
Yeah.
You don't, because usually it will be a black box. We don't even have the access to that if you were to facilitate black box attack.
Right.
Right.
So it's only if so the proxy network we have, we want to train that network to mimic the black box network.
Right.
And then we also want to change the input data so that our input data will eventually.
Right. The input data is basically coming from your proxy network.
Right. Yeah. Okay.
Yeah. Does that answer your question?
Yes. Yeah.
Okay, great.
Thank you. Thank you.
And is there any other question? Okay, I think that's it for today. And we really appreciate your feedback. If you can fill out this 10-second feedback form. And I'll send the link to I'll send the link to the chat channel.
Sure.
Yep.
Actually, so when you apply the update to the image, you change the image,
Right.
so when you're training the proxy model, what's the target? Like what is the label you apply to each
What's the label?
image? Yes.
Okay, yeah, let me share my screen again.
So
You
I
see
think
it?
it's in the slide. Yeah, I
Right.
think it's in the slides right before that one.
Yeah, I see what you mean. Yeah, I think this one, right? Like how to attack.
Yeah.
Yeah. Basically, like your label would be the distribution coming from the black box or the black box network, for example. So let's
Right.
say if you have like two distributions, right? One is like this, like the one above, like cat is probably approximately 70%, dog is like 20%, fish is like 10%.
Yeah.
You have that sort of distribution from the normal network. And what you want to do is feed in an image X. We don't know that image. We want the model to give us the answers. And we result in distribution y of y is equal to f of x. And so we want those two distributions to be far, right?
Okay.
Like the output of y. Oh, sorry.
Yeah.
Basically, output of f is like y, and this distribution, right? Like cat. Let's say if we were to one hot encoded it, that would be like 0, 1, 0, right? I mean, this value is known, right? Because we can just apply the threshold value to the above distribution to make it, anything below, to make it like this. So if we want them to be far, then we can apply this loss function. So L given an X, and the loss function will be minus E, and E is just cross entropy, binary cross entropy. And not binary, sorry, just cross entropy.
Yeah.
And you have two input for the loss function. One is Y. So your one is Y and one is Y hat. So Y would be the output of the network you want to train on, and Y hat would be the output of the original one, right? So the one above here, right?
Oh, okay.
So how to make it as far as possible is just applying a negative sign, right? Because if E, like the function of the cross entropy is small, that means like they're pretty close to each other, right? We don't want that. We want the opposite sign, so we apply a negative sign in front. And for targeted attack, we just add an extra term like Y, like the same Y coming from our attack network, and Y target, like the desired distribution, right? We want to get. So if we, in this case, we want that to be a fish, then we'll one hot encoded it. That'll be the 001. So 100% confidence in fish. And then you go back to here, and your Y target will be 001. And your Y is just your normal like output from the attacking network.
Why do we have both terms and not just the one on the right? Like why keep both?
If you only have one term, let's say if we only have the one on the left, I mean, that's basically non-targeted. And if we only have the term on the right, then that would be basically like approaching to our design. I mean, there's some like trade-offs. It's basically adding this extra term is basically like improving your network's stability based on the non-targeted loss function. It's kind of like regularization, but like we lead it, like we guide it towards that.
So the goal is still to produce predictions that are far from the original model's prediction.
Right. So yeah, again, like loss function. So all we want to do is minimize the loss function. So that means like to increase, let's see, to increase the similarity between y and y target. That's basically it, like why we're adding this term.
Yeah.
Yeah.
I guess I'm a little confused on if we want to increase the similarity between y and y target, why do we keep the value for the similarity between y and y hat?
Right. Yeah. Again, yeah, it's basically an regularization techniques. We can think about it. Like probably this one is from like empirical approach. Like someone did experiment on this, and yeah, because you would have like more loss term.
Okay. And then for the constraint for less than or equal to some epsilon.
Yep.
So how do you run into situations where all of the produced output, does it ever basically converge on one of the corners, for example?
Sorry, what was your question?
Like in the box example that you provided with the epsilon. And then, so this is specifically to fix things. So when you fix the produced image, does just continuing training actually make a significant change to the image, or are you just stuck in the corner? As in, do you have situations where?
Yeah, I see what you mean. Yeah, basically, since like we're updating it step by step, and each step, like each update won't be very large. I mean, it's sort of like overfitting problem. Like we can change our eta a little bit, like our learning rate, right, in order to reduce that effect.